Yeah, hello everybody, and we are still in the exercises of the revision part, and last time we stopped at calculating the variance, and then let's evaluate this integral here. I just cut it, and let's move it here. Oh, and then let's do it like this. This integral is the variance. What do we have to do? So this is the square distance times our f of x. This is x minus mu squared. How do we evaluate this? Any idea? I post this as homework. Well, we could use the product rule, but maybe a little bit easier would be that we just multiply these two parts with each other, and then we obtain from 0 to 4, and this is then 2 minus 8 over 3 x, x squared plus 16 over 9 times 1 half minus 1 over 8x dx, and if we also multiply this, we obtain 0 to 4, and this is then 1 half x squared minus 1 over 8x to the power of 3, and then minus 4 over 3x, and plus 1 over 3x squared plus 8 over 9 minus 2 over 9x. Hopefully you have had also a look at it when I multiplied this, that I do not have made a mistake. Then let's see, here we have the leading exponent with minus 1 over 8 power 3. Then we have 2 times x squared. 1/3 is 3 over 6 plus 2 over 6 is 5 over 6 x squared. Then we have 2 times minus. This is 12 over 9 plus 2 over 9 is 14 over 9 times x, and the last one. So, and then we can take the integrals of every single part of the sum. What is the general integral of minus 1 over 8 x to the power of 3? So this one. Well, it is not helpful if I just do the calculation. What is the integral of x to the power of n? Undetermined integral. Actually, I need a feedback, otherwise it is not helpful to give a lecture. This is easy mathematics from school. So this is 1 over n plus 1 x to the power of n plus 1. So it would be then 1 over 4, so we obtain minus 1 over 32 x to the power of 4. Here it is 1 over 3, so plus 5 over 18 x to the power of 3 minus 2, 7 over 9 power of 2 and 1 half plus 4 over 9 to the power of x within the limits of O to 4. Inserting this is minus 4 to the power of 4 over 32 plus 5 over 18, 4 to the power of 3 minus 7 over 9, 4 to the power of 2 plus 4 over 9 times 4. Well, and this you can do by your own because we want to go a little bit further. Well, still saving. So uniform distribution, and there we had also some little example. Suppose the chief of production within a brewery, and you see that your machine filling a quantity of the bottles is 0.568 liters. But we think that there is a little mistake, and that I think here we have an error by filling our bottles, and this error produces a distribution where we assume that it is a uniformly distribution within 0.556 liters and 0.58 liters. And we want now to calculate the probability that our bottle is filled with less than 0.56 liters. Well, for this we need our uniform distribution. This would mean we have a horizontal line between 0.556 until 0.58. So what is the distance between these two numbers? 0.024. And then we have learned this, the integral over the whole distribution function has to be 1. Here we have a rectangular, and therefore the height has to be 0.024. This is our density function. Graphically, where do I find now the probability up to 0.56? No answer? Well, here is 0.56, and we have learned that the probability is just the integral over the density functions from minus infinity until the value of the limit. So p of x smaller than 0.56 is the integral of minus infinity to 0.56 over the density function. So inserting now our density function, we see we are at 0 until 0.556. We have to calculate the integral of 0.0556 until 0.56 horizontal line 0.024 dx. Well, and this is of course 0.024 times x within the borders 0. This is 56 here 0.0 no, 0.556 until 0.56, and this is 0.004 over 0.024, and this is 1 over 6, so 16 period 6%. This is the probability. Well, we can of course also calculate this by just calculating this area of this rectangular, and this is the height times the length of this interval, which is 0.024. Anyway, what else do we have? Next little example, now using the normal distribution. And this we will quite often use. So let's insert just up this one. Where is here? And there, and let's take 12. Let's delete this. And now you are a CO. This we also do need. In a lamp manufacturing company, and the life expectancy of your LED lamps should be normally distributed around U of 25,000 hours with a standard deviation of 2,000 hours. First of all, you should calculate what is the probability that your lamp works less than 20,000 hours. Idea? Or one. Well, I think it would be always good if you know what you are doing, and for this, graphical imagination would be good. Well, we have already talked a lot about normal distributions. The normal distribution, the standard normal distribution looks like this, and our distribution normally around 25,000 is then just shifted to the right. So our N01 and our normal distribution looks then like this. This is 25,000, and now we want only the probability mass until 20,000. So what we need is just this area here. And what we then do, we want to calculate x smaller than 20,000. And for this, we turn over to the standardized variable. So x to z, and z is now backshifted to the standard normal distribution, where we say that this is x minus mu over sigma, and this is standard normally distributed. This we have shown. So now inserting our limit for x, then we know that this probability equals to z is smaller than 20,000 minus 25,000 over 2,000. And this is, of course, minus 2.5. And for this, then, we have to look in our table, where do we find the probability of x smaller, not x, z smaller than minus 2.5. And for this, we can use the aspect that the normal standard distribution is symmetrical around the origin. And we can use that the probability of, or phi minus c of minus c is 1 minus phi of c. So this is then of minus 2.5 is 1 minus phi of 2.5. And for this, I hope really that you have seen the table for the normal distribution. I have this also here at my webpage, lectures, statistics, and here is the table of the normal distribution. And how do we have to read this table? Well, here is the leading number. So we have 2.5. Going downward here, we need this number and taking down 1 minus 0.99. Since we later on need this, let me just, can I resize this? No. Maybe here, or here, and shift. Let's cut this and paste it in here. So what we need is 2.5, and this would be then this number here equals 1 minus 0.99413 equals roughly 99. Oh, not 99, sorry. 1 minus, oops. Roughly 0.6 if we take this for 0.6%. Have you talked within your introductory course in statistics about the normal distribution and about this table of the normal distribution? No. This is a pity. Then working more than 20,000. Well, this then just would mean we want to calculate this. Well, within the table, we are going up from this to this. So again, we know that the complement one minus the complement is then the probability. So number 2, we obtain that we can say probability of x larger than 27,000 again taking z equals the probability of that larger than 27,000 minus 25,000 over 2,000. This is just 1. That this, so to speak, is the same if we would move here to 23,000, and therefore this equals 1 minus phi of 1. Where is our 1? Within our table, down here, 0.84375 is roughly 18.7%. And the last one, within an interval of 24 up to 28.5. And last color, let's take green. So 24 is maybe here, and 28,500. So we will just need this one. And so this is just the probability from minus infinity up to 28 1,500 minus the probability up to 24,000. So third, the probability of x, of 24,500 smaller than x, smaller than 20, this was 24, 28,500 is then phi of 28,500 minus 25 over 2,000 minus phi of 24 minus 25 over 2,000, and this is then phi of 1.75 minus phi of minus 0.5. Again, we have here our minus sign, and therefore we obtain phi of 1.75 minus 1 minus phi of 0.5, and 1.75 we obtain here, and 0.5 we obtain here. So we have then 0.95994 minus 1 minus 0.69146 equals roughly 65%. Again, my question, and please give me a feedback. This is definitely content of an introductory course of statistics. Have you done something like this in your introductory course? So if you have done it, or it looks a bit familiar, well, this is maybe the core of statistics, dealing with a normal distribution. So then please have a look in your lecture of your introductory course, because I can of course not go deeply again in this topic. Okay, then that it was, and we want then to start with the tasks. Oops, this we do not need. This we need in a minute, but let's now, not only this. Let's produce some empty sheets, and let's have a look what we want to do now together. Oops, the exercise. There I also ask you to have a look inside this. This was, I think, no, not S. This one. Yep. So here we want to do a little bit of descriptive statistics, building a contingency table calculating the relative probabilities, marginal distributions, and then ask from a descriptive point of view if these two things, being the gender, man or female, and working in which industrial sector, in which sector are they, depend on each other. Actually, these are numbers from our statistical office. Well, of course, such a task we shouldn't do by hand, but we should do this with some help of software package, and this, as I already showed you, I will do this with Excel. So move in here and let's maybe shift this a little bit. So then let's take the numbers and hopefully I can, no, I cannot, oh yeah, here I can copy this. And let's see how it looks like if I just directly copy this. Almost. So then let's copy this here and then we move this out and this one, this, and this, this, and this, and this, and this, and this, and this. And this is of course also something like a competence that you hopefully get out the data from the internet as fast as possible. And I think if you do a term paper or some project work, then also quite often you just find a table within a PDF file and then you have to get out the data, and just typing this by hand takes a long time. And what also happens is that you will supposed to do mistakes. So this is then gender and this were man and female. So what are then the accumulated absolute numbers within our sectors, or what are the absolute numbers of man and female? Well, this of course, let's move this here. We have to do just calculating the sum of our columns or lines. So sum of these going down, we have all sums of the sectors and calculating the sum of man and women. And then of course we also can calculate the total sum of our data set. So we have here now 17,929 people. These are the absolute values. And now we want to go to the relative values. What do I have to do when I want to calculate the relative probabilities? So here we want to have what is coming out of my explicit data, the probability to have a qualification in the industrial sector and to be man. What do I have to do? Difference of the sum? I want to have a probability. This should be maybe in percent. So we have 5,256 people which are men and have a qualification in the industrial sector. What is the proportion out of our whole data set? Since we have 17,929 people. You can also talk to me. This would be maybe a little bit faster. You try to talk? Okay. Then maybe I have here the wrong one. Oh, again. Try again.
Hello.
Hello, yes, I hear you.
Okay. So then the 17,929 is 100%.
Yep.
Then 5,256 times 17,929 divided by 100.
So if I would do this, then I would have this and now multiplied this times 100
Divided.
divided. Okay, this is great. And then I'm sorry, this is not your fault because quite often it is written down actually quite often in business administration books that in order to get percentage you have to multiply by 100. And sorry, I have to say this is bullshit. But it's not your fault because it is quite often written down. Because this percent here, oops, here I am, 1% and this percent sign just means is 1 times 1 over 100. The percentage sign means divide the number in front of this sign by 100. So 100% is just 100 over 100 is of course 1. And therefore, in order to obtain your percentage number, you of course have only to take 5,000, anything about almost 18,000. This we fix by $4 signs because now of course we want to divide all our numbers by the absolute value. Why is this not? No, it's working. And then you just have to reformat it that I want to have it in percent. And then I'm done. And how do I obtain the accumulated probabilities?
Just add up.
Yep. What do you want to do? Here,
Uh,
what is the probability to have an overall, no matter if I'm male, if I'm woman, or if I'm man, to have a qualification in the industrial sector?
It is 29,32 plus 5
Yep,
per day.
great. So we can just add these probabilities. This we do for every probability, and here we have to add up these probabilities. Great. Okay, and here of course we obtain then our 100% you have already mentioned. Well, and this is the empiric probabilities. And now within our task, the condition, what would be relative probability? Compare the descriptive results with the theoretical probabilities. So if we assume when our both man, female and sector qualifications, if this would be independent. Do you remember how we obtain these so-called theoretical independent probabilities?
Mhm.
So for this, we have to assume, well, the conditional probability to be in our in one sector and then to be female. In general, conditional probabilities we obtain via Bayes' law. A conditional on B is P of B times P of B conditional on A over P of A. And if we have independent variables A and B, then the overall probability by independence would be just the multiplication of probability A and P. And for this, we have to then multiply the cumulated probabilities in order to get the individuals. So this would be then the cumulated probability to have an industrial qualification. For this, since we later on want to copy this down, times the probability to be man. Fix it, and then we can copy this downward. Oh, here, 24. Oh, I fixed the 24, and I had to fix the G. So here we need the dollar sign. Again, one should know what you are doing when you're manipulating these data, that you directly can check the outcome. And here the same, now directly putting the dollar sign at the right point times the probability to be female. Well, and now taking all our results, now we see here the discrepancy between the empirical empirical and theoretical probabilities. Well, and therefore, we of course have to admit that from a descriptive point of view, we have a hint that these two variables are not independent. Descriptive hint that A and B are not independent. Well, maybe I should also put in here that A is the sector qualification and B is the gender, to be man or female. Okay, so this is just a revision what we have done in the beginning of this lecture. Let's go on. Second question. Well, this is a quite theoretical one. Let's directly take this number 3. Maybe we have time for doing some algebra with Pythagoras, finding a dependence between the different averages we have talked about. But at first, let's do again an example using the binomial distribution. So within a manufacturing process, on average, 75% of the tools are correct, so everything is okay. Calculating the probability that within a sample of n equals 12, you have exactly 3 correct tools. Well, we have again an experiment with an outcome 0 and 1. 1 means again success, so correct. And on average, we have with 75% a correct tool. And this means we have to apply the binomial distribution. And there we had just the probability that out of n, a sample of overall n things, here tools, is binomially distributed. So if x equals some number k, this would be n over k times probability to the power of k times 1 minus p n minus k. And here we have now n equals 12 and k equals 3. and this is 0.75. This we just have to insert, and then we obtain, inserting this, a probability of 0.04%. Calculate the probability that within a sample of n equals 9, we have at least 8 correct tools. Then we have no equality sign here, but we have the probability that x is smaller or equal than 8. And this then just means that we have to start here from k is 0. We have no correct tool until k equals 8. We have 8 correct tools. So this would be then the sum of k equals 0 up to 8, 9 over k times 0.7 to the power of k times 1 minus, 0.25 or 0.75 in 9 minus k. Again, just inserting all this, we obtain roughly 30%. And number C, within the last lecture, I always also inserted this and calculated this by hand. This you maybe should also redo by your own, but in the end, if you know what you are doing, then I would say you are also allowed to just look it up and using some software package. So what is expected value, variance, and standard deviation of our sample when we have now n equals 25? And this is a little bit easier. This actually we can directly calculate by hand. Because remember, e of x for the binomial distribution just means that we have n times p, and this is then 25 times 3 over 4 is 75 over 4. And the variance, remember, there we had n times p times 1 minus p is 25 times 3 times 1 over 16 is 75 over 16. You had the binomial distribution in your introductory course. And hopefully you also remember having done questions like this. Can you just give me a feedback? You have talked about the binomial distribution?
Maybe.
Maybe, okay. So then anyway, take an introductory textbook and please have a look inside, because something like this, binomial distribution, normal distribution, and a uniform distribution. This, I think, when in the end you have your bachelor, you should be familiar with these distributions. Okay, then again, what else we want to do? Number 4, again, normal distribution. So this is then now more or less the same which we have done a minute ago with the example in the lecture. Now just with other mean values and other variances. So, cacao, from experience, we have a normally distribution of 125 grams with a variance of 25 grams. Well, from this normal distribution X, normally distributed with 125 and 5, the square root standard deviation equals 5. This we want to translate into our Z equals now X minus 125 over 5, and this is then standard normally distributed. What is the probability that the weight pack is exactly 125 grams? About this I have also talked in the first lectures. This is somehow a little bit tricky, the answer, because why? Well, we have no discrete variable anymore. And then, of course, you have really to keep in mind having the density function, not the value here, has an interpretation of probability, but only the area within some interval under the density function is interpreted as probability. So to have an exactly value, there we have to admit that this has probability mass of 0. And this, so to speak, was invented around 1900, that you have things which are existing, but they have length or mass of 0. Think also of a derivative where you said the derivative is the limit of these triangles. When you said, well, and then we shrink this capital delta x, the length of the interval, to 0. And then you obtain the derivative. Derivative with length of dx equals 0. Well, about this, maybe you have to think in a philosophical way, that there is existing something with length of 0. So no discrete variable then p of x equals 125 is 0. Now b, I think through this we can go a little bit faster. Drawing again our diagram, f of x, 125, and around it 120, 130. There we learned this probability is just phi of 130 minus 125 over 5 minus the down limit, the lower limit, 120 minus 125 over 5, and then we obtain, this is just 1, or yeah, phi of 1 minus, this would be minus 1, then we again use the symmetry of our distribution function and obtain 1 minus phi of 1. And so we obtain 2 times phi of 1 minus 1. And then let's take our, where was it? Here we had it, our normally distribution table, and phi of 1 is 0.83 equals 2 times 0.841 minus 1, and this I had already calculated. Hopefully is then 68%. C, what is the probability less than 110? This is even a little easier. 110, this would be this. So we obtain phi of 110 minus 125 over 5 is phi of minus 3. So 1 minus phi of 3, and this is down here 0.998. And we 865 even 865, and this is then roughly 0.135%. What is the more than 140? Then we are just here. This hopefully you can directly answer. What is the probability that our package is heavier than 140 grams?
Is it like this first calculation? So
Yeah, for sure. Great. We just use the symmetry, and then of course we have this. Great.
So 140 minus 125
Yeah,
divided.
this we could again, of course, calculate, but since we have already done this here,
Yeah.
and then we do not have to do it again because we can just argue by symmetry it has to be the same. So by probability of x larger than 140 is again 0.135. Great. You are still there. This is really good. Thank you very much. So calculate the symmetric interval. Now we switch it around. Calculate the symmetric interval around the expected values such that with a probability of 95%, the true weight of a pack is within this interval. So, and this later on when we are doing hypothesis testing, this then we will do very, very often. So we know what we want to do is plus minus around our 125. Let's move this just within here. We now say we do not want to calculate the probability, but the probability is given so that this area now is 95%. So E given the symmetric area around 125 as 95%. What are the limits of the interval? Well, here we have this special distribution around some special expected value. But what we know, what we already have, is the standard normal distribution. And there we can say, we can translate this question again into the standard normal distribution, that we now say, what are the limits, these two, when the area here is 95%. And this 5% or 100 minus 95, this is quite often used, and then we quite often speak that if our experiment, our data shows this property, then we quite often say that we have a significant outcome. And because of this, you should really learn or keep in mind these numbers. I don't know if you have participated in the lecture when I did the revision, because this you can just take in your head that if this area under the standard normal distribution is 95%, then you know that you within an interval of minus 1.96 up to plus 1.96. This we can also look up here, 1.9, 1.96. You find just here within the table the 9.7500. And since it's symmetric to the left, oops, this would be half of it, and this would be half of it. So the limits is 1.96 and minus 1.96. So what we then have is, if we say this is, oops, no, it's working. X lower bar and X upper bar. What is X lower bar? Smaller than our X, smaller X upper bar, when this is 95. And for the standard normal distribution, we know that this is plus minus 1.96, and this we can now insert in our standardization that we know the limits are plus minus 1.96. So we have 1.96 equals x upper bar minus 125 over 5. And then we obtain x bar is 5 pi times 1.96 plus 125 is roughly, this is 2, 10, 134 times 8, and x lower bar equals then roughly 115.2, I think. Now we are symmetric around 125. 0.8 and 0.8, yep. Okay, 10 minutes left. Maybe we also can make it with the last one. Because this is now somehow a kind of a mixture between binomial distribution and normal distribution. I don't know, are you also interested in financial markets? Because here I took an example from financial markets. So the annual yield of a stock investment can be approximated to be normally distributed with mu equals 10 and standard deviation of 2. Well, the first one, this we have done now for almost half an hour. We have our normal distribution, f of x, now around 10 and within 8 and 14. So we just want to have this area. So probability of 8 smaller x smaller than 14. Again, remember x minus mu over sigma. We obtain then phi of 8 minus 10 over 2. Sorry, the other way around, because this is the lower limit plus phi of 14 minus 10 over 2. And this is again minus 1. So we obtain, this is 1 and this is 2. We obtain phi of 2 plus phi of 1 minus 1, using again the symmetry of the normal distribution. Again, I need the table. Saving process takes a little bit longer. So this I need again. So 1 we had already sometimes, and this is again here, and now we need also the 2. So 0.97725 plus our known 8.4134 minus 1 equals roughly 81.9%. So assume now we are investing over time and that the yields are statistically independent in every year. So what is the probability that the yields in 2 following years is at least 8%? B, statistically independent. Now yield at least 8%. Let's take this in red. Now we want here the total probability larger than 8%. And this, we know that this would be the same as we would take here the 12 going to the left. So this would be P of x larger than 8 is just our phi of 1. 2 years, statistically independent means again independence. This we had in the other question. Then we can multiply the probabilities. So we obtain the probability is phi of 1 squared, the one we had here, and this is then roughly 70%. What is the probability that the yields in the next 10 years will be exactly 3 times less than 11%? This would be 1 and then 2. 11 would be here. So the single probability would be just the area below the 11, but now within 10 years, exactly 3. And for this, of course, now we need the binomial distribution. Well, and the probability is now the single event to have an yield less than 11. So this is x less than 11. And this is phi of 11 minus 10 over 2 is phi of 0.5. And 10 years, this means n is 10. Exactly 3 times means k equals 3. And using the binomial distribution is then pi of x times 3, and this is here our k is then 10 over 3 times phi of 0.5, 3 times 1 minus phi of 0.5, 10 minus 3. This again we can look up, and this is our 0.69%. And inserting this, we obtain 1.05%. 3 minutes left. One color left, green. C. Which yield can be maximally expected with probability of 99%? Well, this is again the question if we take the look of the other side. So when we start with a standard normal distribution, then we ask for the limit here, x upper bar, when the area from minus infinity up to the limit is 99%. And again, there you can really keep in mind some numbers which we are quite often use in statistics, and the one is the 1.96 for 5% error probability. And then, of course, we quite often take 1% or even more. And where do we have it? Here, the symmetric 9.8% interval means, of course, up to this. This one would be then 1% because this is also 1%, and then the area within is 98%. So up to 2.33 in the standard normal distribution means that the accumulated probability is 99%. And of course, if you want to talk about an error probability symmetrically, adding up to 99%, then the two tails have to have probability mass only of 0.5%, and this number is also a prominent one with 2.58. So knowing this, and sometime then we have just learned this number, we can again insert this in our standardization, and again we have 2.33 equals x minus, what did we have, 10 over 2, and then x bar is 2 times 233 plus 10, and this is 1466, 11.44 landing, and we are almost done. Yeah, maybe over the weekend, because this is really a very nice task. Here you just have to use the Pythagoras a squared plus b squared is c squared. Maybe you find it out. Okay, then thank you very much for today.
Thank